Hello dear students, I hope you're all well. In this short video, you will find some introductory exercises on the discrete probability distributions that you've studied so far. You can find some additional solved exercises on Bboard. Next week, I will also show you how to use RStudio to evaluate PDFs, CDFs, and to sample from discrete and continuous probability distributions, so stay tuned. We will look at an example with the binomial distribution, but first, let's fix some notation. The foundation of the binomial distribution is the Bernoulli distribution. If a random variable x is distributed according to a Bernoulli distribution with parameter p, then x can assume only two values, 0 and 1. The probability for x to be 1 is equal to p, and the probability for x to be 0 is equal to 1 minus p. Recall that random variables are defined on outcome spaces. In this case, you can link the value the random variable x assumes to the outcome of a coin toss. The random variable x is equal to 1 if the toss results in a head. The random variable x is equal to 0 if the coin toss results in a tail. Of course, in general, the coin is biased, therefore, the probability to get a head is equal to p, which in general is different from a half. Through basic calculations, we can get that the expectation of x is p, and the variance of x is p times 1 minus p. Let's assume we have n random variables xi, which are IID, with Bernoulli distribution. IID means independent and identically distributed. Therefore, all these random variables have the same distribution, which is Bernoulli and with the same parameter p, and they're independent between each other. If we define y as the sum of all these Bernoulli random variables, then y is distributed according to a binomial distribution with parameters n and p. As y is the sum of n random variables that can only be 1 or 0, the value of y will be between 0 and n. The PMF, the probability mass function of y, that is the probability for y to be equal to a certain number k between 0 and n, it's equal to n choose k, p to the power of k, 1 minus p to the power of n minus k. It's easy to get the expectation and variance of the binomial distribution. This is just a sum of independent Bernoulli random variables, and therefore its expectation is n times p, that is n times the expectation of a single Bernoulli random variable, and its variance is n times p times 1 minus p, which is n times the variance of a single Bernoulli random variable. Let's look at an exercise on the binomial distribution. Mike teaches 2 sections of applied statistics each year for 30 years for a total of 1,500 students. Each of his students spins a coin 40 times and counts the number of heads. Assuming that each of these 1,500 pennies has probability of head equals 0.3 for a single toss, what is the probability that Mike will encounter at least one student who observes no more than 2 heads? Notice that, in this case, these coins are biased, as the probability of head is equal to 0.3. Let's define the random variable x as the sum of capital N equal 1,500 random variables xi. Xi is a random variable that assumes the value 1 if student I observes no more than 2 heads, and 0 otherwise. Xi assumes the values 0 and 1, therefore it is necessarily a Bernoulli random variable with parameter q. The parameter q is still unknown. However, we define x as the sum of the capital N random variables xi, which are IID and share the common Bernoulli distribution with parameter q. X is the binomial distribution with parameter capital N, q. And we can reformulate our probability, the probability we are searching for, as the probability for x to be higher or equal to 1. The parameter q is defined as the probability for xi to be 1. That is the probability for student I to observe no more than 2 heads. If we define yi as the number of heads observed by student I, q corresponds to the probability for yi to be lower or equal to. As yi is the number of heads observed by student I, we can write it as the sum from j equal 1 to n of yij, where yij is a random variable that assumes the value 1 if student I gets head with the jth toss, and 0 otherwise. Yij is therefore a Bernoulli random variable with parameter p. And we actually know the value of this parameter p because it's given by the question, which is 0.3. Being the sum of small n Bernoulli random variable, yi is a binomial distribution with parameters little n, little p. We can now find q, which is the probability for yi to be lower or equal than 2, and we can calculate it as the sum of probabilities of disjoint events. Q is equal to the probability for yi to be equal 0 plus the probability for yi to be equal 1 plus the probability for yi to be equal 2. We know that yi is distributed according to a binomial distribution with parameters n, p, and therefore the calculations are straightforward. Turns out that q is rather small, as q is approximately 0.0001, and therefore x is a binomial distribution with parameters 1500 and 10 to the power of minus 4. The probability for x to be equal or higher than 1 is more easily computed as 1 minus the probability for x to be equal 0, that is the probability of the complement. After some simple calculations, we get that this probability is 0.1428. Therefore, there's about 40% chance that Mike has at least one student with no more than 2 heads. The Poisson distribution is a very useful and popular distribution which is used to count the number of events that occur in a certain time interval. If the random variable x is distributed according to a Poisson with parameter lambda, then x can take any value in the natural number. The probability mass function of the Poisson, that is the probability for x to be equal to a certain natural number k, is equal to e to the power of minus lambda times lambda to the power of k over k factorial. A Poisson random variable can represent, for example, the number of clients that enter a shop or the number of visitors to a web page. And in general, the Poisson distribution is used to model the number of events that occur in a fixed interval of time, as long as the number of events are independent of the other time intervals and they happen with the mean constant rate lambda. Indeed, the expected value of a Poisson distribution with parameter lambda is lambda, which is also its variance. Let's look at a simple example about the Poisson distribution. What is the probability that a Poisson variable with mean 5 will produce exactly 2 frees in 4 trials? Now, we are dealing with a Poisson random variable, however, it seems like we can sample from it repeatedly. Therefore, we define yi as a random variable with Poisson distribution with parameter 5. And yi represent the ith trial of the Poisson random variable. We are looking at the probability to get exactly 2 frees in 4 trials. Let's define x as the sum from I equal 1 to 4 of xi, where xi is of course the random variables which assumes the value 1 if the ith trial yi is equal to 3. We have that xi is of course a Bernoulli random variable with parameter p, and therefore x, as a sum of Bernoulli random variable, is a binomial with parameters 4, p. We are looking for the probability that x is equal to 2. We know that x is a binomial distribution with parameter 4, p. Therefore, we only need to find p to compute this probability. P is equal to the probability for xi to be equal 1, that is the probability for yi to be equal 3. Yi is a Poisson distribution, therefore we can simply use its probability mass function. The probability that yi is equal to 3 is equal to 0.1404. We now use the probability mass function of the binomial distribution to find that the probability that x is equal to 2 is equal to 0.0874, which is the probability we were searching for. The Poisson distribution was originally studied by the French mathematician Poisson as a limit distribution for the binomial distribution. And indeed, under certain circumstances, we can use the Poisson approximation to the binomial distribution. If x is a random variable with binomial distribution with parameters n and p, it can be approximated by a Poisson distribution with parameter lambda. This can be counterintuitive as the mean of the binomial distribution is n times p. The mean of a Poisson is lambda. The variance of the binomial distribution is n times p times 1 minus p. The variance of a Poisson is lambda. Therefore, the mean and variance of the Poisson distribution are the same, but this is not the case for the binomial distribution. Also, the range of a binomial distribution is between 0 and n. While a Poisson distribution can assume all the natural numbers as values. So the two conditions under which the binomial distribution can be approximated by the Poisson distribution are, first of all, p has to be small. In this way, well, 1 minus p will be close to 1, and therefore the variance of the binomial distribution will be close to n times p, which is also its mean. And of course, n has to be large in order to make the range of the binomial distribution similar to the range of the Poisson. Let's look at a simple exercise on the Poisson approximation to the binomial distribution. A factory produces nails and packs them in boxes of 200. The probability that a nail is defective is 0.006. What is the probability that a box selected at random contains at most 2 nails which are defective? In this case, the parameter n equal to 100 is greater than 50, and p equals 0.006 is lower than 0.1. We can use the Poisson approximation to the binomial distribution. We will match the mean and variance of the Poisson distribution lambda with the mean of the corresponding binomial n times p. Therefore, lambda will be equal to 1.2. Indeed, if we define the random variable x as the number of defective nails in a box, then x is the sum of identically distributed and independent Bernoulli random variable. Each nail is defective with probability 0.006. Therefore, x is a binomial distribution with parameters n and p, and it can be approximated by a Poisson with parameter 1.2. The probability that a box selected at random contains at most 2 nails is equal to the probability for x to be lower or equal to, which is decomposed in probabilities of disjoint events, n is equal to 0.8795. It would have been possible to solve this exercise just using the probability mass function of the binomial distribution. However, especially when n is large, computing the PMF of the binomial distribution is difficult, as it involves calculating the factorial of n. With the geometric distribution, we are dealing again with repeated Bernoulli trials. In particular, the geometric distribution represents the distribution of the first success, the first head, if we are tossing coins. If the random variable x is distributed according to a geometric distribution with parameter p, then x can take as value any strictly positive integer. x can't be 0, as there's no 0 trial. The probability mass function of the geometric distribution, that is the probability for x to be equal to I, is equal to 1 minus p to the power of I minus 1 times p. This is very intuitive, as for x to be I, we need exactly I minus 1 fails, and finally 1 success. The expected value of a geometric distribution is 1 over p, and its variance is 1 minus p over p squared. Let's have a look at an interesting exercise on the geometric distribution. A coin has probability of heads p. There are n players who take turns tossing the coin in round-robin style. Player 1 first, then player 2, then player n, then player 1 again, and so forth. The first player to toss heads wins the game. Let the random variable w, with values in 1, 2, up to n, denote the winner of the game. Compute the probability mass function of w. So it's not clear what the probability mass function of w should look like. However, if we define the random variable u as the first toss that results in heads, well, we know that u has a geometric distribution with parameter p. Now, let I be the winner of the game. So I will be an integer between 1 and n. The winner is I if and only if u is equal to I plus k times n for some non-negative integer k. To convince yourself, think about player I. If the first head happens at trial I, then of course player I wins, as u is equal to I plus kn, with k equals 0. But if the first head happens at trial I plus n, still player I wins, as the coin will have gone round the circle once, and when it's player I's turn, then we have the first head. So u, in this case, is equal to I plus kn with k equal 1. We can express the winner in terms of u in a compact way using modular arithmetic. We could be tempted to write that I is equal to u modulus n. However, the output of taking the modulus n of a number is a number between 0 and n minus 1, whereas the players are numbered from 1 to n in this case. To solve this, we can write, for example, that I is equal to u minus 1 modulus n plus 1. We are asked to find the probability mass function of w, that is the probability for w to be equal to I. This is the probability that u is equal to I plus k times n for some k non-negative integer. This probability can be composed in the infinite sum of the probability of disjoint events. And we can explicitly write out this probability as we know that u has a geometric distribution with parameter p. We can take out of the summation p times 1 minus p to the power of I minus 1, which multiplies an infinite sum from k equals 0 to infinity of 1 minus p to the power of n to the power of k. This is a geometric series whose sum is 1 over 1 minus p to the power of n. This last formula represents the probability mass function of w evaluated at I. For example, in a game with 5 players, if you are player number 3 and the coin is fair, then your probability of winning is 0.1290. There is another interesting way of solving this exercise, which instead of the geometric distribution exploits conditional probabilities and intuition. Think about the event that the winner is I, so that w is I. This event is a subset of the event that the first I minus 1 trials are tails. Indeed, if the winner is I, then the trials up to I minus 1 must have been tails, otherwise the winner would have been someone before I. The probability that w is equal to I can be therefore written as the intersection of the two events, and we can decompose it using conditional probability. For ease of notation, let's define Pi as the probability for W to be I. Pi is equal to the probability for the first I minus 1 trials to be tails, that is 1 minus p to the power of I minus 1, times the probability of W to be I, given that the first I minus 1 trials have been tails. This probability is equal to P1. This is true because of the memoryless property of the coin. Player I's probability of winning is now equal to his probability of winning at the same game where he plays first. We define this probability as P1. This is the key intuition to solve this exercise. We have that Pi is equal to 1 minus p to the power of I minus 1 times P1. We can obtain P1 using what is called the boundary condition. W is a finite discrete random variable, and the sum of the probabilities of all its n possible outcomes must be equal to 1. First, we substitute the formula for Pi in terms of P1. We then write the sum of this finite geometric series explicitly. Turns out P1 is equal to P over 1 minus p to the power of n. Once P1 is found, it's easy to calculate the explicit expression for the probability that W is equal to I, and therefore the PMF of W. The result is of course the same as what we got previously.